So we're gonna, just like we revisited this idea of Q versus 1 over T curves in area and under, giving you an idea of the change in entropy, whether or the entropy added or entropy removed from a system. We're gonna revisit this, the PV curves. So pressure is one of these intensive independent, right, properties that can be used to describe the state of a system. When you couple it with the volume of the system, we get ideas about the boundary work. So revisiting the work done on the system, boundary work, PV, and if I want to put this in integral form, it's minus the integral of P dV. Whereas in terms of the first law, Q equals delta U minus the work on the system. Now I could write it in, I could put it in integral form in the context of the work by, and that is just simply you get rid of the minus sign and it's P dV, and then the first law instead in equation form would, in a simplified equation form, would look like such. So just straight from that, the work by equals the minus the work on. So let's consider some process or a cycle where there's two different processes. So I go from, let's just say this is a really simple engine, okay? And, or let's not say it's an engine, right? Let's say it's some type of process and it's unknown, but somebody measured the pressure and volume of your system. So you want to know whether work was input or output. And so you have the data, but that's all you know. And that's all they want to know is, okay, this is secret. All I want you to do is calculate whether it's work done or work by, or whatever it might be. So you have this, and you have some process that goes from state 1 to state 2, and then it goes back, it goes from state 2 back to state 1. It's a cycle. The area under the curve represents, we know, either work on or work by. I already gave you that clock, you know, the clock analogy to calculate it, so you can just do that right away. But let's say you don't know that. Let's assume you don't know that. And we want to calculate or know the work on the system. So we don't really know, is it work on the system or work by the system? So the best thing to do is just assume one of them, say work on. So assume work on. So then we take work cycle and we use this negative format for the integral. So work cycle, and we'll assume it's on. So that's going to equal the integral from state 1 to state 2, taking path 1 to 2, plus the integral from state 2 to state 1, so there's a typo there, plus the integral from state 2 to state 1 in the minus form, right? So this represents work on for that path, this represents work on for that path. So work on, and if I do this, okay, if I just do a simple way just to get a number, so 2, these are all positive values, let's say. 2 is greater than, V2 is greater than V1, so I got some positive pressure times a positive thing, so, and then I have a minus sign, so I end up getting a minus, a number, 1 to 2. And then I want to add the second part, but now V1 is less than V2, right? So I end up getting a negative number, so I have a minus times a minus number 2 to 1. So the work on the system, because the magnitude of the number we get from the calculation from taking path 1 to 2 is greater than the magnitude of the number we would get from 2 to 1. So that means we have minus, right? This number is greater than this number. So we have minus sine times the area within the cycle path curve. So we got a negative number, right? We assumed it was work on, and we ended up getting a negative value. So that means that it was actually work by. We guessed wrong. So if we were to guess right and we got a positive value, then, so just, that is, if we guessed right, then calc would have produced a positive answer. So that's just a quick demonstration that if you don't know, all we need to do is take the the formalism for the integral of work on, then calculate it, and given that we started with the work on, we should always expect a positive number. And if we end up getting 0, then there was no work on or by. And if we get a negative number, then it was actually work by the system. And in this context, this is work by the system, and it does follow the clockwise, right? Work by the system. I put my finger, the clock hand moves my hand, and the clockwise, it's work on me, right? It's work by the system. By the clock on me, or by the engine, or by whatever it might be. Right? So first law, energy conversion, energy transfer. Written the first law in the same format we just did. Conservation of energy, right? Energy of the system plus the energies of the surroundings has to equal a constant. If we're looking at, so it has to equal a constant, so if the energy of the system increases, the energy of the surroundings has to decrease. So here's my block diagram of some system. It has an internal energy. Let's put the box around it to represent the boundary. And I have an internal energy. Instead of writing E sub int, I could just put a U. Just different nomenclature, right? And so I have my system, and in the context of what we've discussed so far in detail, I've talked about other forms of energy transfer, but the three primary ones are heat, work, and mass. So I can have heat that is exchanged or transferred between my surroundings and my system. I can have mass transfer, and I can have the transfer of work, energy in the form of work. So just kind of refresher on what we've talked before. So for an isolated system, just draw a block diagram of an isolated system. And in here, I have some internal energy at a given state. And sometime later, right, it might have another internal energy at some, right. But I have my system. So if it's an isolated system, Q equals what? How about the rate of mass transfer?
0.
How about work?
0.
So that means that delta U equals,
0.
yeah, so it's just a quick refresher that I have my system, it's separated from my surroundings. If it's isolated, it doesn't even know it has surroundings. It's isolated. There's no communication. So if we consider, right, some information as with the unit of energy, then there's no information transfer. A closed system. So a closed system, what is Q? It's not equal to 0. How about the mass transfer in a closed system? And how about work?
Not 0.
Yeah. So that implies that delta U is not equal to 0. So in principle, in general, the only way you really get, you can get a balance where you don't get a change in internal energy. But one thing is for certain, usually your internal energy changes between two states if it's not an isolated system. So just a long-winded way to write it out, the change in energy in my system, which I could also write this as U, right? My system is everything inside the boundary. So given that I have a boundary, everything inside is internal. So the change in internal energy, or the change in energy in my system, equals all the forms of energy in minus all the forms of energy out. Okay. And I can put this in rate form. Likewise, delta U dot. The rate of heat in, the rate of heat out, work in, work out, mass in, mass out.